evening, and welcome to our second Google Hangout, Exoplanet Explosion. I'm happy to have a whole lot of you with us today, readers and viewers of Astronomy magazine and Discover magazine, and we have a distinguished panel of guest commentators today. I'd like to introduce to you the editor-at-large of Discover, Corey Powell, who comes to us from Washington, D.C., where there's lots of exoplanet news going on with the American Astronomical Society meeting. And Corey is coming fresh off of a birthday. Happy birthday, Corey.
Well, thank you.
And with Corey is Sarah Scholes, our associate editor at Astronomy. She's also at the meeting there. You can see them in Washington. And we also have associate editor for Discover, Bill Andrews, who is also an alumnus of Astronomy magazine. He's across the building from me now. And we're all going to talk a little bit about exoplanets and then take your questions. So let me just get started by saying that the subject of exoplanets has been around for a little while now, because the Greek philosopher Thales of Miletus in the 6th century BC was the first one to bring up the concept, the idea of the plurality of worlds, that there could be many worlds out in the universe like our world that we don't know of. Now, it took until 1991, however, until astronomers discovered the first exoplanet, and that was a planet orbiting a pulsar. Then a number of years later, in 1995, the first normal main sequence star with a planet was detected around this planet around the star 51 Pegasi. And since then, we've discovered a whole lot of planets outside our solar system, orbiting other stars near us in the galaxy. There are now 1,000, roughly, that are known, in some 800 and change systems. And the Kepler satellite, which is still a little bit in limbo, we'll talk about that a lot, which has been operating for the past couple of years over a very, very small patch of sky between the constellations Cygnus and Lyra, and not looking terribly deep into the galaxy, really for the most part only a couple of hundred light years away, discovered about 3,000 additional exoplanet candidates. So there are a whole lot, if you can imagine, you extrapolate that number out into our entire galaxy, which has approximately 400 billion stars, and then all the galaxies that we know of in the universe that amount to about 125 billion galaxies. Astronomers are trending toward the notion that there are a tremendous number of planets out in the universe around other stars. So what we're going to do is talk about a whole bunch of different aspects of extrasolar planets today in a whole lot of different ways. And let's get started with the reason why we're holding this today with both Sarah and Corey, because there's a lot of news about a variety of very interesting extrasolar planetary systems coming out of the AAS meeting in Washington. So if you would, Corey and Sarah, give us a little bit of an update about some of the exciting news.
Want to start?
Sure. Yeah, I think maybe I'll start with my personal favorite, most exciting discovery, which was that astronomers found a planet that is exactly one Earth mass, but it's really different from Earth because it's 1.6 times the width of Earth. So obviously, if it's the same mass and 1.6 times bigger, it can't have the same composition. So they actually found that it has this really thick, gassy atmosphere around it that is hundreds of miles thick of hydrogen and helium, which is, you know, we're always looking for planets that are Earth-sized, but this is just more proof that they're not necessarily always Earth-like.
I think, to me, yeah, I think probably the most exciting trend that I've been seeing over the past few days is two incredibly unsexy things that are producing very sexy results. One is data mining, and the other is improving signal to noise. And these are both, you know, they're both technical ideas, and they're both about as boring as it gets, because it's the real nitty-gritty of how the science is done. But what those things let you do, data mining means basically exactly what it sounds like. You dig through all the different information to find the things you want to find, and the Kepler Observatory in particular has an enormous mountain of information that it just takes a long time to find what are the things in there that are interesting. And signal to noise is basically what then lets you look at these planets and learn things that just a few years ago seemed impossible to tell. You know, not just how large are they, but you know, how dense are they? What are they made of? Do they have atmospheres? What are the atmospheres made of? Do they have clouds? So all of a sudden, these things, these things that are not even dots of light, they're dots of darkness against a bright star. The fact that you can know anything about them is amazing. And yet, the past few days we were hearing about one planet that seems to be covered with clouds of potassium chloride, which is sort of like a you can buy it as an alternative to salt for people who are on low salt diets. It's an entire planet covered with fake salt. And another planet that is there are actually a whole series of planets that are a little bit bigger than Earth, but seem to be two completely different kinds of planets. Some that seem to be rocky planets that could have oceans and clouds like our own. Others that are big puffy planets that have no analog in our solar system. So basically, we found a whole new class of planets. So all of this is, it requires a lot of time. It requires a lot of very tedious analysis. But what comes out of it is that we're learning. Basically, we're learning whether or not our solar system is a freak. We're learning whether or not the Earth is the freak. And what we're finding is that there actually is an incredible diversity of planets out there, and every single planet that we're being able to study in more detail is turning out to be a unique individual.
Right. Every planet is a freak. In other words, is what we've learned at this conference.
Yes, we're all special and we're all different.
And we're learning about the incredible diversity of exoplanets, despite the fact that we really cannot yet detect Earth analogs effectively. But we're looking at a range of things, mostly that are between super Earths and mini Neptunes when we talk about very small planets that are being discovered. And of course, the instrumentation and technique will get us to finding, we believe, lots of true Earth analogs. But there was an interesting paper from a day or two ago, I think, wasn't there, at the meeting from Nick Cohen about, do super Earths really look like Earth? What was that something that intrigued you in this inventory of going from hot Jupiters very close to their stars to things that are a little bit more terrestrial and very varied?
Yeah, Nick Cohen and his collaborators asked each other, he said they turned and looked at each other and said they wondered, do super Earths have continents like Earth does? Because traditionally astronomers think that these super Earths, which are 1 to 4 times as massive as Earth, would be covered in really huge oceans, and that any land that might be beneath them would just be totally submerged within these oceans. But they ran these models that discovered that actually the high gravity from having such a massive planet would pull a bunch of the water from the surface and the crust down into the mantle of the planet below the crust, so that the ocean level would actually be lower and land actually could be there. And then actually, when they were talking about it, someone asked the question, well, if aliens could live on this planet, even if they could walk around, wouldn't they be crushed from the huge amount of gravity? And Nick actually made the point that fighter pilots undergo more G-forces, about 3 G-forces, which they experience on that planet. And he said that critters are, alien critters are tougher than fighter pilots, so they'd be fine.
Bill Barucki, who is the head of the Kepler project, and so he's probably one of the people more than anybody else who's really responsible for finding this incredible diversity of exoplanets. I asked him about this in a recent interview, and he said, "Well, the gravity on these super Earths might be twice of what the gravity is on Earth, but I weigh twice as much as I did in college, and I'm alive." So I thought that was a pretty good answer.
Life lessons from the American Astronomical Society conference.
That's great. Well, let's talk a little bit about Kepler, and anybody jump in if you'd like to, but there's so much excitement about Kepler as the greatest planet discovering machine, and then all of our collective extrasolar planetary hearts were broken this past year when Gyro died, and in effect Kepler died. But now there's a plan that's being discussed there really to resurrect the telescope, isn't there?
There is, yeah. It's called K2, and so Kepler is staring at this really specific field of the sky, or it was before it was broken, and it has to be very precise in where it's pointed. So the trick is, if it doesn't have these wheels that can put it back in the right spot, how is it going to do that? And the Kepler team actually came up with a really clever plan to use the photon pressure from the light coming from the sun as a wheel to balance the spacecraft, as if it were the third wheel that Kepler is missing.
So right, so the idea is it's not yet a funded and approved extension, but what this would let you do is basically switch Kepler back on, start looking for planets all over again in a different direction, in a slightly different way. But the most important thing is if you're looking for a planet that's exactly like Earth, it takes a long time to do that. Earth takes 1 year to go around the sun. The way Kepler looks, it looks when it finds a planet when the planet passes in front of the star. Well, if you're looking for a planet that's just like the Earth, you're waiting a year for that to happen. And if you want to see that happen 2 or 3 times to be sure you're not making a mistake, obviously you're talking about 2 or 3 years of looking to find one Earth. So so being able to run the mission for a longer period of time is incredibly important for finding planets that are not just a little bit like the Earth, but that are really exactly like the Earth. So that's the real excitement of being able to extend the mission.
Mm-hmm. And the scientists still do have a bunch of data that they're not finished going through. So even though this mission isn't funded yet and it hasn't started yet, there's still going to be more new discoveries announced throughout the rest of this year, at least.
Absolutely, because Kepler has really discovered 134 exoplanets in 76 systems at this point, but there are 3,000 candidates just from Kepler, as we mentioned before. And let me just interject, we've got a lot of ground to cover here, but viewers, if you'd like to send us questions, you can do that, and we'll be answering some questions mostly a little bit later on, either on the event page itself or using the Twitter hashtag exoplanets. You can send us questions. Let's take one good question that we have now, and anyone can jump in on this. This is from Mark Walton. Except that I almost lost it there. Quick technical challenge. There we go. Mark Walton sends us a question. If we look at our own solar system, we only get a transit of Venus twice every 100+ years, as our orbital planes don't align. Does this mean that we could be missing many exoplanets for similar reasons, especially the small rocky ones?
Yes.
Yes. So, I mean, the longer answer is basically to see any planet, Kepler has to get very, very lucky. So for exactly that reason, the vast majority of the planets, I think it's like between 98 and 99% of the planets out there are going to be invisible to Kepler for that reason. And so Kepler looks at a huge number of stars, at nearly 150,000 stars, or at least it was looking at those stars until it lost its aim. You have to look at a lot of different stars and watch them very, very carefully. And that's again what I was saying, that there's this data problem. That's why there's this data problem. You just think of it, if you're trying to look at 150,000 things at the same time, looking for just a little blip of light when a planet passes in front of it. That's the technical challenge that Kepler is doing, and the fact that that people are able to find, as you say, over 150 confirmed planets, over 3,000 apparent planets. That is. You have to step back for a second and think about the technical challenge. It is astonishing that people can do that. And for many, many years, scientists thought it was impossible. This team went up against a lot of reviewers who told them that what they were attempting was ridiculous and they'd never get funding for it. And yet now here we are. I also want to explain just quickly the difference between a candidate planet and a confirmed planet. So Kepler sees these little blips of light, but doesn't have the ability that a big telescope on the ground has to look at it in detail and just make absolutely sure to actually measure the star, measure what the star is doing, and be sure that that blip really is a planet. So probably most of those 3,000 plus candidates really are planets. They just haven't been through all the follow-up observations you need to say scientifically, yes, I'm sure they're.
Right. Yeah, I think in the upper 90s percent-wise of the candidates end up to actually be planets. Just not bad. That's an A.
And just to mention again, the field of view of Kepler is so tiny. It's about 10 by 10 degrees on the sky, which is a little square in between the constellations Cygnus and Lyra. And as I mentioned, it's also not looking out very deeply at all, of course, into the galaxy. So if you extrapolate that, it's one of the interesting things that if Kepler is in some way can be slightly refunded and redirected to a new piece of sky, that's going to be pretty exciting, just looking at a new slice of sky in that way. But you can imagine that the numbers just explode and that there could be, as some astronomers estimate at Harvard and elsewhere this past year, many billions of even Earth analog planets just in the Milky Way galaxy. So the numbers are quite amazing. Bill, I wonder if you can kind of pick up on what Corey was saying, and why have exoplanets only recently become a big deal, just the last few years really, in terms of astronomical research?
Sure. I know that's something actually my wife asked me the other day. She's like, why is exoplanets up in everything now? I never really heard about them more than 10 years ago. And as we've alluded to, more than 10 years ago, there really weren't that many that we knew about. It was, as I think you said, Dave, just a theoretical idea for the longest time, and then in '91 they found that one crazy pulsar planet, and then in '95 they found the other ones, and it was kind of the slow trickle, because you can imagine finding a little tiny world, a speck of a speck, against all these other stars would be a really hard thing. And so it's only really in recent years, starting at the turn of the century, the 2000s-ish, and especially with the launch of Kepler, that we were able to get any kind of a good grasp of just how we can physically do this kind of observation, being able to find these blips of light, the transiting planets across the face of their star. And I think I heard it said that it was something, it's akin to seeing the shadow on a headlight of a car, miles distant, when a housefly, buzzes in front of that light. That's about how much the light of this star drops. So Kepler and the other recently available kinds of technology that can detect this are what's making this kind of recent boom possible. So, it's exciting times. A great time to be alive and into exoplanets.
Well, very lucky.
And let's follow that thread again. And again, let me remind viewers that you can submit questions on Twitter using the hashtag exoplanets, or post them on the event page that you're on Google. But here's a question from Paul Smith. So on page 13 of the February 2014 Astronomy magazine is an article about exoplanets orbiting white dwarfs. It says the only way to see what distant planets or asteroids are made of is to break them apart. Corey just talked about our knowledge of the composition of exoplanets. How can that be true?
I'm glad you asked. So this is one of the really just kind of mind-boggling bits of scientific detective work that's been going on with exoplanets. So now, seeing that dot pass in front of the star, which we were saying was the difficult thing, that's now the easy thing. Now imagine if, while that dot is passing in front of the star, you're looking for starlight going through the atmosphere of that dot, or seeing some light reflected off that dot as it just passes off the star and a little bit to the side. There are now ways to look at that, to actually subtract out the light of the star, so that you're only seeing the light that's passed through the atmosphere of the planet. And from that, you can actually start to learn what the atmospheres are made of. We're still at the very early stages of that, but getting to the point where you can see which planets have clouds and which ones don't, which planets have hydrogen or water in their atmospheres and which ones don't. It's a very small number of planets we can do that for, but we're starting to get to that. The other thing that you can do, which is really interesting, is you can figure out a lot just by knowing the size and the mass of the planet, which lets you figure out its density, and then you can run computer models of, well, what kind of a planet could that be? Some of these planets are as dense as the Earth, or denser. There's one planet that's like as dense as lead. Well, that tells you that can't be a big ball of gas. That can't be a big ball of ice. That has to be rock and metal. There are other planets that are puffy. There's one they call the styrofoam planet. I mean, there's some that are they're less dense than water. And so again, you know the kinds of things that are out there that a planet could be made of. Those have to be planets that have big puffy atmospheres that are made of relatively lightweight materials. So the answer is some of it is indirect, is just indirect inference, but some of it is really quite direct, actually looking spectroscopically at what a planet is made of. It's doing forensic science of that fly passing in front of that car headlight miles away. So now you're not only confirming that the fly is there, you're actually basically studying is there some dirt on the wing of the fly passing in front of that headlight? It's amazing.
And sometimes there's a cool result from Laura Kreidberg at this conference where they actually didn't see the dirt on the wing of the fly that they thought they should see, stuff that they knew pretty much had to be in the atmosphere of this particular planet. And because they didn't see that, they were able to infer that clouds were actually blocking them from seeing these molecules that were there, which is pretty cool. Like, I think the difference between this conference and maybe the past few years is that now we've moved on from we found some planets, that's awesome, to here's some stuff we can learn really specifically about these planets and how they may or may not be habitable, or how they're like Earth or not like Earth.
Right, that particular planet, it's called, unfortunately, most of these planets have boring names. It's called GJ1214b. So there are a few things interesting about it. It's just a little bit larger than the Earth, and it's only a little bit warmer than the Earth. So it's the closest thing that we've seen, both in size and temperature. It's the closest planet to the Earth that we've been able to study this way. And unfortunately, we were hoping, you'll see, an atmosphere that looks like an Earth-like atmosphere. In fact, it seems to be covered with clouds. And again, based on detective work, not on direct detection, but just on detective work, that's the planet that the researcher thinks might be covered with potassium chloride clouds. But what this tells you is we're just on the cusp of being able to look at planets that really are Earth-like in size, Earth-like in temperature. And if you're going to find signals of life on another planet, that may be the way you do it, is you find an atmosphere that looks like the atmosphere that life would produce.
And so much of this, as you all have said, is driven by the magic of spectroscopy, which we're really not concerned with hard rock investigations of asteroids, but with spectroscopy and analyzing the light, we can travel across the universe. We know that chemistry behaves similarly everywhere we look, observationally, and we can determine what's really going on in very distant places through that fantastic technique. And we mentioned very interesting and odd planets that are out there. I wanted to bring up another favorite of mine, and that is 55 Cancri E, the so-called diamond planet, which we know is a planet that's approximately a little more than 8 Earth masses. But it's so dense that astronomers can infer that it must have, and it's also very carbon-rich, exceedingly carbon-rich, its spectrum, so that we can infer that it must, in fact, be a planet that is largely made up of a mantle of diamond with a graphite crust. And so there are all kinds of really weird things that are going on out there with some of these planets that we can get into as well. But let's go to another question if we can, and this is from Tony Angel, a great observer and imager and astronomer. The past 20 years saw the growth of amateur astronomers discovering supernovae. Do you see the next 20 years as a time when amateurs start to hit similar numbers for the discovery of exoplanets? Does anyone want to give a go at that?
Sure. Well, I mean, the truth is, it's already starting to happen. To find transiting exoplanets where you're seeing the shadow of a planet in front of its star, what you need to do is you need to observe the light curves very, very, very accurately. So you basically just need an electronic detector, electronic light detector that's very well calibrated. Especially for brighter nearby stars, you don't need a particularly large telescope. In fact, some of the planets were discovered with 4-inch telescopes, with things that are not even very advanced amateur telescopes. So yes, I think a lot of the problem right now is sky coverage. As you say, Kepler is only just looking at one tiny part of the sky. The big observatories can only look at a few candidates at a time until the next big observatory called TESS, which is not going to happen until I think 2017. Yeah, I think 2018 when it'll actually start returning data. Until then, one of the big problems is just knowing where to look, and amateurs definitely have a role there to help add the sky coverage of looking for these transits.
And I mean, what made Kepler so different from any other exoplanet search is that it was totally dedicated to finding exoplanets. So if you were an amateur who's totally dedicated to finding exoplanets, you can do more of that than another national telescope that has to do everybody's projects and different things. And just as a side note, the Kepler team, the K2 resurrection mission, they announced here that all of the data that comes from that, if it does get funded and go through, will be public. So anyone could just go get that, look through it, see what's going on.
Are they actually calling it K2 the resurrection? Because if they're not, if they're not, they should. Okay, K2. If it's from here on out, it's called K2 the resurrection.
I think there's a movie screenplay in the works here for that. And, you know, it's funny because years ago, everyone used to say in the professional community that, well, amateurs can contribute to science and help us out with this and blah, 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 blah. Excuse me. And it was, you know, it was the situation that the telescopes and the CCDs were not really good enough. Well, now, for about a decade, they have been. And you really can contribute real, definitive data that professional astronomers will take and use under the right circumstances. And, of course, amateurs have one thing that no other science has, and that's the same sky that the professionals use. And they also have time, and the time of professional astronomers is very limited, as well as the projects that they're working on in specific targets and with big telescopes. So amateurs can step in and play a role in that same way as they did with supernovae 10 or 15 years ago, in that they have a lot of telescopes, good CCDs now, and a lot of time. Now, Bill, let me throw a question your way, if I may, to continue on this track of what's out there near us near the solar system in the galaxy. So much of this is driven by our desire to find out about life and how rare it is and how special we are or not, and so on. And that's the case with water on Mars and our feelings about exoplanets and could they be habitable. What does it matter if some distant planet is in the habitable zone? I mean, is it really a big deal? We know of exoplanets now in habitable zones. How should we be feeling philosophically about the meaning of stepping out and discovering the rarity or the commonality of these worlds and what it means to living on this little planet Earth?
Sure. Well, I mean, I'm glad you gave me an easy question. Philosophy.
I like to save those for you.
Yeah, exactly. Thank you. I mean, I just hope I get the right answer. I don't want anyone to correct me on philosophy.
The nice thing is that there is no right answer.
Exactly. And, I mean, for me, I think part of it is just kind of how can it not be interesting that we have we're almost at the means of being able to find a planet that we can determine through our detective work can host life, that there might be, you know, the chemical signs of life on that planet. That would be really cool. I mean, if you're into this stuff at all, if you like the thoughts of looking up and appreciating the beauty and knowing what you're looking at, knowing that there's other life in the universe, I mean, that's pretty fundamental. I just feel like philosophically, how can you not? But even more specifically than that, scientifically, it's also a valuable question. It tells us a lot about you know, some of the other disciplines that are related to the universe, biology and chemistry, which, as we know, chemistry and physics don't change anywhere, but do they apply everywhere? Is there biochemistry happening in other worlds? And if so, what kind of equations, what kind of chemical reactions are happening? And if we know that, that will inform us about our own biology, our own interesting, you know, place in the universe and being able to put things in greater context. So, I mean, you've got just the fact that it's cool. You've got the idea that it informs us about who we are and what life might be. And speaking of philosophy, what is life? You know, that's pretty cool. And at the same time, I feel like you've also just kind of got a pretty good approach with being able to get other people excited about this too, that while I feel like astronomy is one of the better sciences for getting people interested in this stuff, the idea that you can go over to someone and say, you know what, we have this ability. We think on that little light up there in the sky, there are life forms. That, I mean, just as a kind of as a recruitment tool is also, I think, invaluable because it gets at what people really care about. Everyone is alive, I think. Robots not excluded, of course, but it's something that we can all share and that we can all get behind, and it's useful to find out and learn these things just for all these different reasons. But again, for me, I think it's just cool. It's just so cool.
And I mean, it's it's cool that we are alive when you can do this. I mean, as Dave pointed out about people thinking about exoplanets and, you know, life on other planets has been happening for thousands of years, and everyone has been wondering, and we're just now getting to the point where we can say, yes, there are other planets. Here's what their clouds are made of, and that's really cool to be alive right now.
Yeah, I think, you know, for the last for the last 50 years, the assumption was, well, if there's life somewhere else, you know, the way we're going to find it is by going to Mars and looking around. And I think there's a pretty good indication now that you know, if we find life elsewhere in the universe, we may find it through chemical evidence, looking at planets around other stars, before we get a real answer one way or the other on Mars. And you know, I think in terms of, you know, what that means to me, I think, you know, first of all, look, there's a basic human condition that, you know, everyone's, you know, born into this world alone. We all die in this world alone, and you're always trying to figure out, you make connections to other people and find out, you know, what is my place in the world. This is the same, you know, it's the same thing writ large. It's what is our place in the universe. You know, is Earth a unique place where something happened that didn't happen anywhere else, or is there really something about the universe that is inherently inclined to create life? And you know, if you find life one other place in the universe, pretty much as soon as you find it in two places, you know, nothing happens twice that doesn't happen a million times or a billion times or a trillion times. You know, I think if you find it anywhere else, that tells you this is a living universe, that we are, you know, that we are the result of a process that is universal and that's somehow inherent in the way the laws of physics and chemistry are built. And that to me is just, you know, I mean, it's a philosophically and emotionally incredibly rich thing to know that that's, you know, either answer is very profound.
And I mean, on average, in the history of astronomy, we usually find out we're not special and we're not that important. Like the sun doesn't rotate, or you know, the sun doesn't orbit Earth. The sun is part of the galaxy. We found out there are many other galaxies. We found out the universe is getting bigger, and that generally these laws apply everywhere. And so, I mean, it makes sense to me, at least, that it would move in that direction for planets and life. Also. Right.
In this case, not being special is actually probably the more exciting answer.
Right. I want that answer.
Yes.
Yeah.
And of course, we know from observing the universe that matter combines the same way everywhere we look, spectroscopically and elsewhere, and with our own experiments here, that atoms are attracted ionically with electrical charges to other types of atoms and combine in very specific ways. And that process presumably works the same way throughout the universe, all the evidence suggests. And also, the more we've looked at what we believe to be analogs or examples of extremely simple life on Earth, we refine our view that it's easier and easier and easier to get life going than people imagined many years ago, and also to have it survive extraordinarily difficult and challenging environments. So the suggestion, the implication is that life perhaps may be very easy to get going in many, many places throughout the universe. And we have some other good questions I'd like to step in from viewers with now. But before we do that very quickly, because this is leading up to the next question, forgive me, but let me just read off the 9 detection methods that can be used to discover extrasolar planets. And of course, the first few are by and large vastly the most important ones, but there's of course the radial velocity method or Doppler method, transit method, as we've talked about with Kepler and with other upcoming projects, gravitational microlensing, astrometry, that is the precise positions of objects of variations due to a planet, pulsar timing, orbital light variations and relativistic beaming, ellipsoidal variations caused by massive planets slightly changing the shape of a star, polarized light detection, and circumstellar disks. So this exciting review leads up to our next question, which is from LabRoots.
You're missing a couple.
And LabRoots has a question. Transiting planets is one method being used. What are the best methods for detecting planets? Gravitational wobble, gravitational lensing, direct observation, etc.? Question mark.
Well, look, the thing that you really, really want to be able to do is direct detection. What you want to be able to do is put a telescope in space point it at a star that you know has an Earth-like planet around it, look at that Earth-like planet directly, and get observations. That's how you would find out, for instance, if that planet has has oceans and continents. That's how you would find out exactly what that planet is made of, and that's probably if we ever are going to find evidence for really good chemical evidence for life on another planet, that's probably what it's going to take. That would let you look for something like, oh, like this planet has methane and oxygen in its atmosphere. The only way that can happen is if there is some active process that creates both those things, because they're not stable otherwise. That's one of the sort of like the magic combinations that the astronomers want to look for, that they would consider a sign of biological activity. You need a space telescope. It's a multi-billion-dollar mission, and you also need to know where to look. We don't actually have good candidates to look at just yet for that kind of a telescope. But that's what we're working toward. I mean, there are many ways toward that. There's a mission called WFIRST, which is under proposal right now, and if you combine that with a second component that basically would blot out the light of the star and let you look at nearby planets, that would be an incredible mission for starting to do that direct detection. And that again, that could happen somewhere around 2023 or so. So we're about 10 years away from potentially being able to do that. And honestly, if people approve the money for that tomorrow, it could happen sooner than that. It's really, it's a question of getting the money and developing the technology, not of fundamentally not knowing how to do it.
Mm-hmm. Another cool kind of detection method that people have been talking about here at the conference is called transit timing variation, which is a way to detect planets in multiple planet systems. So the transit, you're just watching for the planet passing in front of the star and blocking some of the light, but you can also measure whether its orbit appears to change in time, like whether it changes slightly, and that change can tell you whether there are other planets that are tugging the planet and changing the time of its orbit a little bit. And they've been talking a lot about that, and for detecting other planets in star systems where they know there is one planet and they wonder if there are more.
Yeah, that's another. It's an amazing kind of sort of bootstrapping technique. It's the way the planet Neptune was discovered in our solar system, but it's basically applying what astronomers did here about 150 years ago, applying that to systems that are a million times further away, a million times further away.
That's great. Now let's go to a question from Rich Gruber. With all the exoplanets having been discovered, has SETI found any candidates to zero in on to look for signals of intelligence? So is there yet, what's the burgeoning relationship between exoplanet discovery and the search for extraterrestrial intelligence? That's ambitious.
Why don't you let Bill answer that one?
Oh yeah, another easy one. Yeah, cool. Well, I'll tell them where to look too while I'm at it. Over there. I mean, as far as I know, since I am slated to answer these big questions, there hasn't been any good candidates for intelligence. As far as I know, we haven't really found any great candidates for life as we know it, outside of our solar system, of course, and even within it, even Earth for intelligent life. Sometimes I wonder. So it's something that, again, we're kind of on the verge of. I feel like within the next decade or so, hopefully we will be seeing something that will be that they'll be able to make use of and directly go for this ETI, the intelligent part. But even until then, I'd be pretty happy with just finding life out there too is a pretty nice first step that I think we're really closing in on too.
It's okay. It's an okay step.
Yeah, if I can just add to that quickly. So I mean, one of the things that we're seeing, especially from the Kepler mission, because it's really collected all these statistics. What we're seeing is that it looks like almost every star has planets, and we always sort of suspected that, but now we have a pretty good inkling that almost every sun-like star has planets, and that so far the current statistics are something between 15 and 20% of those stars have Earth-like planets in the habitable zone, and that's actually a lower limit. If you think about, an alien looking at our solar system would probably say that we have 3 planets in the habitable zone. Venus, Earth, and Mars are all sort of, possibly in that realm. I suspect that you're going to find something like that is true in general. That there are probably more potentially habitable planets out there in our galaxy than there are stars in our galaxy. They're probably, they're probably like 200 or 300 billion potential habitable planets. So from a SETI point of view, it's good news and bad news. It means there are a lot of different places, but it also means if you want to guess which star could have an Earth-like planet, the answer is every single one. So it doesn't. We haven't really found the one that tells you yet. Oh, look at this star and not at that star.
And just a quick interjection, I do know that the SETI Institute did have a project using the Green Bank telescope, kind of as a proof of concept, where they looked at some of the Earth-sized planets that Kepler first found. It was a couple of years ago, and to just see if there were any radio signals coming from them that looked intelligent. And I assume they'll continue that as planets are less Earth-sized and more Earth-like as we move more in that direction, which is exciting.
Oh, and as an aside, the Green Bank telescope is probably going to lose its funding. So if there's a billionaire out there who wants to turn the Green Bank telescope into a SETI project, now's the time.
It only costs $10 million a year to run.
Oh yeah, it's a bargain. Yeah, you don't
I would do it.
Get in at the ground floor. Start now at the cusp.
Corey, I would say that based on the last week of weather in the Midwest, I'm coming to the conviction that Mars is definitely habitable in the zone. Now we have a good question from John Hugg, and this ties into a talk I believe that happened a couple of days ago at the meeting. Any detections of moons around exoplanets? I read that might be possible, and I think it was David Kipping who, Sarah, I think that was in your blog as well, who gave a talk about the attempt to discover moons and finding small exoplanets with his research.
Right, that very, very first result that I mentioned at the beginning of the Hangout, where it was an exactly one Earth mass planet, was David Kipping, and he was looking for exomoons, and that's how he found something so small. And he was using that the transit timing variation where other planets tug, and he thought that he could see a moon tugging on a planet, but what he actually found was a smaller planet instead.
Right, he found a planet that's actually just about a little smaller than Mars, a little bit larger than the Moon, significantly smaller than Earth, and it is by far the smallest measured exoplanet that we've seen so far. But so far no moons, but that's an incredibly difficult observation. So it's not surprising that they haven't found it yet.
Do we know enough yet? And I know they're preliminary and they're in the works and they're not operating, obviously. But can we talk a little bit about TESS and about CHEOPS and the next sort of wave of exoplanet missions, one from NASA and one from ESA and partners, and what they may do in terms of taking us into a new frontier of discovery?
Sure. So Kepler, we were describing earlier, Kepler is sort of narrow and deep. It looks at one part of the sky. It looks very, very deep. And what Kepler was designed to do was look at a lot of stars and basically collect statistics. They picked a part of the sky at random and said, okay, this is a perfectly random patch of sky. These are presumably representative stars. Let's try to find every single planet that's out there in that group. So Kepler goes narrow and deep. TESS can go broad and shallow. TESS will scan the entire sky, but will mostly not be able to see these very long period Earth-like planets that take a whole year to go around. TESS will for most of the sky, TESS will only be able to see things that are in a 1 month orbit or shorter. But what TESS will do is it'll look at much brighter stars, much nearer stars, and cover the entire sky. So what TESS will do is actually find really good candidates, really interesting places to look that then the observatories on the ground that have the luxury of not running, they can keep running and running and running. They're not limited by time. Then observatories on the ground can go and do follow-up observations and see these things in detail. So they're baby steps. Kepler told us that the stuff is out there. TESS is going to tell us where to look, and then the real step is after that. Once you know what's out there and where to look for things, then you can launch a mission where you go and do very focused studies of look at this one planet and try to figure out, could this be a place where things are living?
And here's another good question from Rich Gruber. Isn't the Webb Space Telescope, when operational, we hope it will be operational, supposed to see these exoplanets as well?
when it gets up there. They can look at them. They do plan to use James Webb to follow up on things that TESS finds.
Yeah. So what's interesting about Webb is so Webb will definitely be able to extend these studies of the transiting exoplanets, looking at atmospheres and looking at what they're made of. The kinds of planets that you really want to look at, again, the planets that are sort of like the Earth in size and temperature, are probably just beyond what the Webb telescope can do. So it will tell you a lot about some of the more extreme types of planets, and we'll learn a lot. But it falls just short of doing that very, very specific type of precision that you need to look exactly at an Earth-like planet.
Excellent. And here's a good question from Gordon Gould. What will it take to get a 90% plus confidence, excuse me, in detecting biosignatures on an exoplanet? What would you all consider the biomarker or markers that would give you confidence the planet had some sort of biological activity? Lots of cows wandering around in methane.
Cows.
Actually, yes. Flying a drone over, taking a picture and seeing a bunch of cows, that would be very convincing.
Mm-hmm. I would be convinced.
Yeah.
Even if they were space cows, I'd still count it.
Yeah. For space cowboys. I mean, the serious answer is, I mean, there are a number of researchers. Sarah Seeger at MIT is probably one of the lead people doing that. Who are they're actually running through the theory of what would different types of atmospheres look like, and what would the molecules that we think of as associated with life look like in those atmospheres, and how would you find them? So, but the reader who asked that question asked in a very perceptive way, which is you're not going to get a 100% definitive answer. You will get something like a 90% confidence. So that was a great question that way. What you're going to see is it probably will be something like we see. I mentioned earlier we see methane and we see oxygen, and there's no way that could happen without some active process that's creating them. We think that's life. It's going to be a kind of a frustratingly circumstantial thing. But if you see a planet that has a signature of oceans and a signature of continents and a signature of oxygen and a signature of methane, and you see all those things, that would give you a very, very high confidence that you're looking at a living planet. And again, we know how to do that. I mean, we're probably about 10 years away from being able to do it, but we're very, very close.
And then cows.
And then cows. Yeah.
Yeah.
Well, the cows make the methane.
Right.
And hamburgers, too.
Yes.
Here's a question from Mel Head that's a very good question. Is there any correlation between the number of exoplanets found by star type? Where are astronomers preferentially looking toward solar-type stars, for example?
That exists.
What?
I don't actually know it off the top of my head, but Kepler, the telescope, its mission is focusing on solar-type stars.
Well, yeah. So there are two kinds of biases. There's the human bias here, which is we want to look at stars that are like the sun, and then there's also a bias that's built into the universe, which is that the universe makes a lot more small stars than big stars. So the bright hot stars when you look at Orion, or you look at Deneb, the bright star, and Cygnus, those bright hot stars that look really good in the night sky are extremely rare. We see a lot of them because you can see them from far away. In fact, most of what's out there are small, cool stars, things that are called red dwarfs or M dwarfs. And so there are different programs. Some programs look for stars that are especially like the sun. Some programs, like David Charbonneau at Harvard, is specifically looking at these M dwarf stars because if you want to think about where are most of the planets out there are probably around these incredibly abundant small, cool red stars. And the question is, can life exist around those stars? Do they create the right kind of planets? Do they create the right kind of conditions? That would be a really interesting question because that's probably where 80 or 90% of the planets in our galaxy are.
And the feeling early on was that there wasn't so much of a chance that life, or at least advanced life, civilizations for a long period could exist around red dwarfs. Now there's sort of a wave coming back among a number of people feeling that you could have long-lived perhaps even civilizations around red dwarfs. So that sort of reawakens as you say, Corey, the most numerous by far count of stars in the galaxy.
Yeah, I think one of the big lessons from the past 15, 20 years of searching for planets is nobody knows anything. Anybody who tells you, this is how it is, this is how it has to be, this is what this is where life can or can't be. What's been really exciting is that each time people look, they see things that they didn't expect. In fact, they not only see things they didn't expect, they see things that previously the theorists assured them could not exist. So any prediction of where life can or cannot exist, I wouldn't believe any of that.
And in terms of what's been discovered to the question answer, not necessarily what's out there, because obviously we have our biases about what we found, but the website Exoplanet Encyclopedia, you can actually make a plot showing how many planets have been found around what type of star. So you can do that.
That's absolutely right, and I'll make one self-serving plug for us here, and that is we have a very good friend of the magazine, Seth Shostak, who's at the SETI Institute. He did a recent article for us about smart life around red dwarf stars. It's in the February Astronomy, which coincidentally, we didn't plan this at all, happens to be on newsstands right now. So that's out there as well. Bill, let me ask you before we start to run out of a little bit of time here on the clock, what's your favorite exoplanet and why?
Oh, well, it's so difficult to choose. They're like all my children in a way. But I do have a stock favorite because occasionally people ask this, and my answer is the catchily named HD 209458b.
Oh, that's a good one.
Yeah, thank you. I'm very proud of it personally. It's one of the hot Jupiter kind of planets that they were all the rage a few years ago because they were, as it turns out, among the easier ones to detect. So the first bunch of exoplanets that they were able to find, they were able to do a lot of stuff with, were these so-called hot Jupiters that are very close to their stars and very big. And this particular one, 209458b, is great because it was right at the forefront. They found it in '99. They discovered it probably has water vapor in it. They discovered what the temperature is like on it. They were able to do all these nifty new techniques for it. And when this was all coming out about 10 years ago now, that it was really, this is one of the planets to know about. It was one of the things that also helped turn me in this direction a little bit because I found it so fascinating. This just, oh, they found a planet. Oh, they know this about it. They know that about it. They can do this with it. And for some reason, 209458b also just kind of feels musically very nice to me. So that's my favorite. But I don't know. You guys were already talking about some of yours too. The Diamond Planet, and I mean, we all have our favorites, I'm sure.
Yeah, so somebody really needs to get on the job of giving these planets better names. There's a bureaucratic problem that nobody has actually nobody's assembled the committee to approve and designate names for these planets, and so they have horrible letters and numbers that you have to remember. And people want to call them oh, I love Wrigley's Pleasure Planet. Now that's a good planet.
Yeah.
So I'm waiting Wrigley's Pleasure Planet is awesome.
It is an awesome planet.
Awesome.
Yes.
I have actually heard that my favorite 209458b, there is a movement underway to call it Osiris.
Yes.
Which is very cool. I mean, I like that name too. I don't know among whom this movement is very strong. I don't think it's the scientists.
It's on Wikipedia.
Yeah, exactly. So it must
It's got to be true.
Can't argue with Wikipedia.
There's a whole other hour discussing what to believe on the internet and the fact that books still exist, actually, and are factually correct, but we won't go there. I would have to say Alpha Centauri b, although it's not known to exist at a level of 100% certainty because of the pushing the technology right up to the limit of what you can detect. But the fact that there may be a kind of a neat heavy Earth, about 10% more mass than Earth, 4.36 light years away, and in the closest star system to us, that's pretty cool too. And of course, those numbers of quasi-Earth analogs, although this is a hot planet, we expect will explode over the coming years. Let's go to another question for all of us here. What's different? What's new and different about the latest crop of exoplanets as opposed to all those that we've talked about for a year or two from Kepler? Is there anything really new and exciting coming out at the meeting or over the last few weeks that gets you going?
Well,
we haven't talked about already.
I'm going to say something general.
Yeah,
so I'll go first, and then you can go specific.
Absolutely.
Just that we've been seeing a lot of statistical things that they're able to do now that we know of more than 1,000 confirmed exoplanets and have these other candidates. You can do the kinds of population studies that allow you to separate distinct types of planets, like talking about earlier, where you have the kind of rocky things that are a little bit bigger than Earth, and then the ones that have huge gassy atmospheres around them, and separate, like, this is a distinct type of planet, this is a distinct type of planet. And when we were just discovering a few planets and we didn't know very much about what they were actually like, it was hard to tell, as we said, what was a freak and what wasn't, and now we kind of know, well, they're all freaks, but they do kind of fit into categories.
I totally agree. One of the more exciting things of this meeting was actually, was then actually picking apart, this whole taxonomy of planets, because you see planets that are about the size of Earth, planets that are twice the diameter, 4 times the diameter. As they get bigger, at some point, some planets are actually physically like the Earth, and some planets, at a certain size, they're big enough that they probably become more like Neptune. They become like big gassy things that are not pleasant places to live. And this meeting, one of the really interesting results was that they've actually found the dividing line, that they know planets that are up to twice the diameter of the Earth seem to have compositions that are similar to Earth. They seem to be rocky planets with thin atmospheres. We don't know if they're habitable, but we know that their basic construction is like our planet. Planets that are bigger than that have big puffy atmospheres and are probably not places that could support life. So just having enough information to start to say, oh yeah, these are the kinds of planets that are interesting for being habitable. These are the kind of planets that are interesting scientifically to tell you stuff about how planets form, but they're probably not places to look for life. The other thing, which is, it's not quite planets, but it's related to planets, is brown dwarfs. And there's been just amazing results here about brown dwarfs. These are things that are sort of halfway between a big planet like Jupiter and a very small star like a red dwarf. And they apparently have intense weather systems and giant storm systems and clouds of molten iron and snowflakes of 1,000-degree silicon snow. They're bizarre, and studying how they work, they're a little bit easier to study than planets, and but they share a lot of characteristics. And so studying these things and seeing the strange things that they do is actually it's a great learning experience of how to study the planets, and they're just such wonderfully strange things in their own right.
And if you would have said a few years ago that you would be able to study and detect weather on a brown dwarf, people would have thought you were completely out of your mind. But that's really an incredible development. Let's just go back to what we're learning about the sizes of planets and the samples of exoplanets that have been found thus far. And it's really interesting because it does also conversely kind of confirm our ideas, in essence, about how we think our solar system formed as well, which is kind of neat. But right now we have an inventory of exoplanets that's approximately the following. 72% of them are Jupiter-sized, 15% are Neptunes, 11% are super-Earths, 0.7% are roughly Mars-sized, 0.3% are Mercury-sized, and 1% of those are, 0.1% are Earth-sized. So that, taking that and taking what we know about the inventory of stars in the galaxy, quite a number of astronomers this year, there was that famous Harvard announcement, have sort of proposed an idea of a number of something like 40 billion Earth-like planets in our Milky Way galaxy. Let's finish by just reflecting on that, if you will. What if there are 40 billion Earth-like planets out there, and a fair number of those, at least a small fraction, are in habitable zones? What does that say to us about our galaxy and about the meaning of life in the universe?
Bill,
that's a Bill question. Bill, I didn't want you to kick that one off.
Yes, thank you. The meaning of life in the universe, I think that was established a few decades ago as being 42, if I remember correctly. But otherwise, I think it just kind of sums up everything we've been saying. These are exciting times that we're able to know these things, that maybe the Copernican principle keeps going forward. We're not as special as we think. You know, there's planets everywhere. Maybe there's Earth-like planets. Maybe they're habitable. And in fact, if that study's correct, there are way more than we think. Contact had that one quote, the movie Contact, about, you know, there's all those stars and all, if just one of them in a million, just one in a million, there'd still be millions left. And I don't think the math worked out in the movie, but the principle is the same. It would be a colossal waste of space if it turns out all that possibility, all those probabilities are out there, and we are still unique in the universe. It's possible, and we might find that out, and that would be interesting. But, I mean, for me, it's also kind of one more nudge in the sense of, well, maybe we will find kind of what we're looking for, the sense of life, of extraterrestrial, maybe intelligent life. Who knows? But that's just what I think. I don't know. What do you guys think?
Well, you said it pretty well.
Oh, thank you.
I'll add it. I mean, just from a living in the world perspective, it's cool to go out at night and look at the stars and think, wow, so many of those stars probably have Earth-sized planets around them, which is not something you could think necessarily 10 years ago and know that you were correct. Maybe not all the stars you can see, but, you know, in our galaxy, they exist, and it changes your personal view of the universe, I think.
Yeah, I think no, I think Bill said it very nicely. You know, honestly, I think 40 billion is a conservative number. I think the number is probably bigger than that, but in a sense, it doesn't matter what the exact number is. The point is that there are so many different opportunities out there where the conditions could be like the conditions here. You're going to learn something either way. You know, if we look at all those planets, it turns out that, you know, there are, you know, all those billions of opportunities and none of them created life, then something happened here that was astonishingly different than anything else, and you want to know what that is. And the flip side is, if you find that the galaxy is full of living planets, then you know that you know, we as humans, we as living things are participating in something that is what the universe does. And I think, you know, I think either one of those answers is really, you know, it just completely changes the way that you think about your, you know, why we're alive and why we're here and what we are a part of. You know, we're either a part of a big system, or we're something that really stands apart. And either one of those, to me, is a, you know, a mind-boggling advance.
Well, that's a great way to finish, and you know, it's taken 2,600 years, but we finally got to the point where we're closing the loop on Thales' original question, the Greek philosopher who was really the first person on Earth to make the assertion that observation was the way to gather knowledge. His ideas about the plurality of worlds have been around for a long, long time, but now we have our first good ideas. We're starting the inventory of where we are with this around us in our galaxy, near us in our galaxy, and we have a lot of work to do and a long way to go, but it is indeed a very exciting time. Thank you, Corey Powell. Thank you, Sarah Scholes. Thank you, Bill Andrews. Thanks to all of our watchers and listeners and the folks who sent great questions into us. I'm Dave Eicher, the editor of Astronomy. We'll see you on our next Google Hangout at some point here in the near future, and I thank you all for joining us and wish you a good rest of the week. Goodbye.